Okay, tomorrow we'll have our test over this unit, this fun unit with all those application problems, right? Um, as you have experienced working through the problems, they do take a while, and so we're going to cut back on the number of problems on the test. There's actually a huge number of 10 problems on the test, which, well, that means each problem is worth that much more, but there's lots and lots of steps to them, so just be careful. I will definitely be grading very carefully and making sure you at least know the general process. If you do that and just make little mistakes, it won't hurt you too bad. You will be allowed one sheet of paper. That's 8.5 inches by 11 inches.
That's just like a normal piece of notebook.
Yeah, normal piece of notebook paper. I don't want
Every single exam.
yeah, you guys might come in with 8.5 feet by 11 feet. Well, that's a little too much, but get your units on there. As I take points off for missing units. Definitely in this section, this unit, you're going to need some units on your answers, or at least in some parts. Some parts it's just from a graph, and we're not really worried about is it feet or inches or meters or stuff like that. So, but lots of formulas to get down, and if you need to write down some examples of problems, that's fine too. But one sheet of paper. The integral tables, I will allow you that too. We already were tested on all those integration techniques, so you don't need to show me you know how to do those anymore. Well, you should know how to do those still, but that's not what I'm testing you over. So, and some of these, especially when you get into the arc length and those kind of things, those tables become very important. And as usual, you can come in early or stay late, whatever time-wise you need to do. It is designed for an hour, but I know some of you get stuck on one problem and spend 30 minutes on just one problem, and then, or maybe more than one problem. But anyway, yeah, time flies when you're having fun, right? So. Well, for the sections that we covered, the first section was actually not really on an application, but what we call improper integrals, and be able to state whether they converge or diverge, and if they converge, what number do they converge to? A common form of an improper integral from 1 out to infinity. And let's see, we'll just pick a real straightforward one here. Technically, our integral limits cannot be infinity, so we would have to say, let's take the limit as b, will allow b to be some value, and say, well, it's going to approach infinity of the integral from 1 to b. And from there, integrate integral of 1 over x is what? Okay, natural log of x, we're going from 1 to b. So then we have this nice little limit at the end of the natural log of b minus the natural log of 1. And, well, natural log of 1 is what? 0. So the focus here, natural log of b as b approaches infinity, what can we say about that? Okay, that will go off to infinity. So we say this improper integral diverges. Okay. Now, if it had equaled some number, then we say it converges to that number. And I will have something about if it converges, what does it converge to? So be able to find the number as well. What other type of improper integral did we run into? Okay. Something like 0 to 3 and x, or integrating 1 over x minus 1 or something like that. Why would this be an improper integral? At x equals 1, we would have 0 in the denominator, so technically we would have to change this into integrate from 0 to 1, and then plus 1 to 3, and then turn it into a limit, this time not b approaching infinity, but for this one we could say b approaching 1 from the left. A lot of times that doesn't matter whether it's from the left or right, but we need to keep that in mind. I'll just kind of running out of room here, but b approaching 1 from the left, and then integrate from 0 to b. And then this one, it doesn't matter if you say b or a or whatever. Normally we treat the bottom limit as a and the top one as b. So in this case we'd have the limit as a approaches 1 from the right, looking at the interval from 1 to 3, so anything a little bit bigger than 1. So limit as a approaches 1 from the right, and then integrating a to 3 and work through that. So those can be a little sneaky because it almost looks like just a definite integral when we identify just that part of it. But always make sure you look, is there an x value in the interval where this would be discontinuous? And then separate it like we did there. Okay? So that's your improper integrals. I guess with our handouts that was 8.8. Any questions about those? Yeah.
Let's say it was from 1 to 3. What we just do one single limit instead of splitting it up? Was that the limit from a equals 1?
Yeah, this last part would be the limit as a approaches 1 from the right, and then the integral would be from a up to 3. I guess we could put the dx up there. So your integral would be separated into two parts. One, the first one where the very highest possible value would be your 1, and then the second one, a would approach 1 from the right, would be your lowest value in that interval. Okay? Okay. Other questions on improper integrals? Then we jump to the idea of the average value of a function. Over a certain interval. And that might be the easiest section we looked at for this unit. But the average value, what's your formula for that? Do you remember? Okay, 1 over b minus a. Okay, and then the integral from a to b of your function. And geometrically, what we can think of, this would represent the area under the curve from a to b, and then the b minus a is really the length of the interval that we're talking about. So average, we think of adding up all the numbers and dividing by the number of numbers. Well, with function, continuous function, the concept is similar. Adding up all the values, well, when we integrate, we're technically adding a whole bunch of areas together, and then we're dividing by the, well, length of the interval. So similar idea of average of the numbers, but with a continuous function it's a little bit more involved. But again, once you have this formula, it's probably the easiest thing you'll see, well, maybe all semester. But yeah, you want 3 or 4 of these, right? Probably not. Probably 1, maybe 2 of certain problems, but this one probably just 1. Okay, any questions about average value? Well, the next concept, we kind of looked at a few different sections in our online material. Finding the volume of some region being revolved around, well, some axis, x-axis, y-axis, the line x equals 6, the line y equals 4, something like that. And we spent several days on this because there's a couple different methods to use, and one of these is called the disk method. And then using the disk method, once in a while we ended up with a hole in the middle, which the disk method can sometimes turn into a washer. And then we extended to a different technique, still finding volume of a surface of revolution, but using the shell method. Now, by the end of the shell method, we were given problems that said find the volume, use whichever method you want. Now, I'm not going to say use this method or use that method on the test. I'm just going to say, here's your region, revolve it about this line, find the volume. You can decide, well, is the shell method easier? Is the disk method easier? What may be easier for you may be difficult for somebody else. So I don't expect all of you to do the same technique on each one of these problems, but that'll be personal preference. But yeah, probably one type of problem would be geared more towards the disk method being easier. One may be geared more towards the shell method being easier. But I think pretty much all of these, both methods could be used to get the correct answer. Okay, so I'm not going to look for one or the other. It's just give me the right answer. If you get the wrong answer, then I'll go back and see where you made your mistake. But that's going to be up to you which one you decide is easiest for you. If you recognize what the easier method is, that's great. But if not, doesn't matter. Okay? Questions on that one? I guess the disk method was from your handout 7.2 and shell method 7.3. So we did quite a bit on those. So again, probably a couple of them, maybe 2 or 3 of the volume. Okay. Next up, we looked at the arc length, and this again is your formula. Basically, ds or s would equal integral from a to b of what?
Square root of 1 plus x is the derivative of s.
Okay, square that derivative and then dx. Now, the derivative was probably the easiest part on this, but then plugging that in, squaring it, adding 1, and then taking the square root, yeah, those problems get a little bit ugly. Probably quite a bit of simplifying, algebraic simplifying in this type of problem. So, setting it up is important. Doing the algebra is important too, but I'll be looking at mainly, did you set it up right? If you got a wrong answer, then I'll try to find where you made your mistake, but probably something in the algebra. That as you work through those, I think all of you found the algebra to be really fun, right? Or something like that. Well, in this section, I also added the surface area, taking an arc length and then revolving it about either x-axis, y-axis, then looking at the surface area. Kind of like your volume problems, except it's just a curve that we revolved, which made, well, a kind of a shell of it wasn't a solid three-dimensional object, but just a shell of a three-dimensional object. So surface area, well, the formula for it will be very much like what we looked at for arc length. We think of the surface area formula 2 pi r and then times your ds. So I guess we could say delta A, we develop the formula this way, the area of that little slice we looked at was 2 pi times your radius times delta S, which again integrates 2 pi, well, the r, sometimes the r represented the x value, and we just put in x and then times the ds times the square root part. Or get your ds in there. Sometimes the r represented the y value. So it would be the y equals whatever your function was to get your curve. So you'd plug in the function instead of just x, and then times that square root. And I think most of you probably found these calculated easier as integrals than the arc length did, because that little x on the outside, or f of x, whatever that was taken care of by letting u equal the inside of the square root, and then du would take care of that outside part. So, little less algebra on those. It looks uglier, but integrates a little bit easier, usually. So, okay, questions on that? And those came from our handout at 7.4. Then from our handout of 7.5, we talked about work, calculating work, and for a constant force over a straight line, the basic formula for work is force times distance. But we found that sometimes the force was not constant over the distance we looked at. With the springs and also with rockets propelling objects up into space, force of gravity changes the farther away from the Earth's surface. So sometimes we had that. Let's see, for the spring, we had force represented here, and your K is your proportionality constant. You're given information to where you could find K and then use that for your force function. And for the rocket propulsion, easy for me to say, huh? That was essentially our, Newton's gravitational force. The force is proportional, inversely proportional to the square of the distance from the surface of the Earth. So, and in doing that as well, to find K there, we needed X, or X would represent the radius of the Earth, and your radius of Earth is approximately 4,000 miles, close enough for our calculations. So, make sure you have that written down on your piece of paper. And then one other work problem was how much work is done in pumping, emptying out a tank. Maybe we're pumping a tank out the top of a tank. Well, in that case, we'd have to take a slice of the tank, and the force would basically be representing the weight of that little slice. And force is volume times density. And the density of whatever we're pumping out, I will give you that in the problem. Water, 62.4 pounds per cubic foot. But if we have a problem like that, I'll give you the density of the liquid. That represents the force, and then work also involves the distance, so you got to figure out distance as well. Okay. So 3 basic types of work problems. Any particular questions on those? And our final topic, which came out of 7.6 on our handout, center of mass. he kind of approached this a little more basic than what I would usually do, but center of mass, the calculations are the same, but he pretty much talked about just the center of this region. Mass is area times density. And of course, the regions we were talking about, we always dealt with a constant density. So in the end, it didn't matter what the density was because of the way the formulas turned out. Density canceled out in the fraction form. But now I want to kind of take a little bit farther than what he talked about. The center of mass, he said, was basically 1 over a and then times the integral from a to b of x times f of x dx. Well, this part right here would actually be representing what we call the moment about the y-axis. And some physics terms, you engineering majors will be dealing with moments a lot in a course called statics. But moment is a tendency to rotate about a point or a line. In this case, it'd be the y-axis. And moment is calculated by mass times distance, okay? Directed distance. It's basically, think of your teeter-totter, kids playing on a teeter-totter. If one kid is bigger than the other kid, can they balance on the teeter-totter? Well, it depends how far from the middle or how far from the fulcrum they are. The bigger kid would have to be closer than the smaller kid. So by that, they could balance. And that's a very simple illustration of a moment, but that's essentially what we're talking about here. X represents the distance from the y-axis, and then f of x dx would represent area. Well, mass is density times area, and where the density is a constant, okay, and in the handout we use the Greek letter rho, kind of look like a P, but it's Greek. But we'd have rho times all of this, and then in the denominator, instead of area, we really would be calculating total mass. Well, mass, again, area times density. So it'd be A times that constant density. So with the constant density in the numerator, the constant density in the denominator, they cancel out, and so x bar can simply be written this way. Now, what he talked about was the function over the x-axis. But in our handout, we kind of went beyond that a little bit with maybe some region, or this is one region, and this may be another region. And to kind of find the center of mass of that region, we can think about, well, we've done area between two curves back in Calc 1. Area is f of x minus g of x, and then times your delta x or dx. So this right here would change to just f of x minus g of x. So we'll go ahead and change that form. which this formula works for what we saw in the videos as well. G of x just turned out to be 0, being down to the x-axis. The big problem, though, y bar is a little bit more complicated than this, with a region between two curves. It's going to be, well, the 1/2 will be multiplied by f of x quantity squared minus g of x quantity squared. So that would be the formula for y bar for a region like this. And that's a little bit of extension from what you're used to seeing from the video. But we may have something, find the center of mass with constant density of a region between two curves. So definitely have those on your note card, and make sure you know how to use them as well. That always helps. Okay? Questions out of center of mass, out of that section?